Well, good afternoon, everybody. I'm David Darling. I'm Dean of the School of Engineering and Applied Science here at GW, otherwise known as SEAS. On behalf of the faculty, the staff, the students of SEAS, I'd like to offer you a very, very warm welcome today. I'm happy you can join us in this very special celebration we're having. We have many distinguished guests here today, and I can't call you all out by name, so I apologize, but I would like to recognize members of the GW Board of Trustees who are here today, and they include David Karlgaard and Terry Collins, and former trustees of the university, Mark Hughes and Emilio Fernandez. So thank you, gentlemen. I'll point out that David Karlgaard, Terry Collins, and Mark Hughes are also members of our National Advisory Council. Mark Hughes is the current chair. Also here today is the former chair of our Advisory Council, who's looking at me right now, Randy Graves. Welcome. I'd also like to recognize Provost Stephen Lerman. Steve played a very key role in helping us establish the new department and helping us recruit the new chair, Igor Efimov, who I'm going to introduce shortly. So I want to say a big thanks to Steve. Where is Steve? I'm probably looking at him. He's over the other side. Thank you, Steve. And I'd also like to recognize the strong support of President Knapp. He could not be here this afternoon, but he also played a key role in supporting and promoting the creation of BME. I also want to express my gratitude to two other individuals. The first is somebody whose name I've already mentioned, Trustee Terry Collins. I'm happy to tell you that Professor Efimov, the new chair of the BME department, will be the first holder of a new endowed professorship established by Terry and his wife, Alisanne. So we're very, very grateful to Terry and his wife for creating this professorship. There'll be an official installation of Igor into this endowed professorship in March. I also wanted to thank, and I was hoping he and his wife would be here today, but they couldn't make it. They live in Florida. David Wang and his wife, Cecile. We are, however, recording this event, so we'll be able to put it on the web or send them a DVD, so be aware of that. So if you're going to scratch your ears and look around, you're going to be on TV at some stage. In the summer of 2013, which is about 18 months ago, David and Cecile learned that we were planning to create the new BME department. And they realized immediately that doing this is going to require seed money in a number of different areas. And they provided us with a significant gift, which is being used over the first 4.5 years of the department to really facilitate its development and accelerate its growth. And these funds are going to be used for graduate student fellowships, a distinguished speaker series, an annual BME day to showcase our faculty and student research, supporting a biomedical innovation lab, and also for seed funding for collaborative research efforts inside and outside of GW. And saying that word, thinking of collaboration, leads me to welcome Lynn Goldman of our Milken Institute School of Public Health, and Jeff Ackman, who is Dean of the School of Medicine and Health Sciences, and also Dr. Guillermo Gutierrez, Professor of Medicine, Anesthesiology, and Engineering, I may add, and Director of the Division of Pulmonary Care, Critical Care and Sleep Medicine in GW's MFA. And these are some of the schools and divisions, there will be many more, with which the faculty and students are going to be collaborating on with research projects as we move forward. Well, today we are here to celebrate the launch of a brand new BME department, and we're doing it in a brand new building, which we moved into in late December, early January. I don't know if you're a visitor today, you've had a chance to look around before you came in, but after the reception, I would encourage you just to walk around and see what we have here. I think you're going to be really, really impressed. I have not met a soul yet who's come into this building and left without saying, oh, wow, what a place. The word I've been using lately, a single word to describe what we have here, is fabulous. It's a little Hollywood-like, but I think it really is. This is a fabulous facility. And one thing about it is absolutely certain. It's going to be a really true enabler of remarkable things, not just for BME, but for engineering departments and the sciences. So what could be better than this today, launching a new department in a new building and introducing a new chair? And let me add, we're doing it in the what is called now the Lehman Auditorium. This is named in honor of Donald Lehman, who was Executive Vice President for Academic Affairs here at GW up until 2010. And he served 38 and a half years here at GW, by the way, and he recruited me to GW, so I have a great fondness in my heart for Don. And I'd like to add that, I'll add a word of thanks. This room is named in honor of Don Lehman, following a substantial gift from somebody I already mentioned just now, Mark Hughes, former trustee and current chair of our advisory council. And this is going to be an ideal space, as is obvious, to host seminars, workshops, panels with our growing roster of collaborators inside of GW and outside of GW. After my introduction of Professor Efimov, he's going to give a short presentation of his own research interests and expertise, and then he's going to moderate a panel discussion. And this panel will really try and help us all understand the evolution of biomedical engineering nationally and also here at GW, and the role and the unique place of biomedical engineering and biomedical research in general in the generation of new intellectual property in biomedical innovation and in the growth of the biomedical engineering or biomedical device industry. And of great importance to our department's success, the panel is also going to talk about the truly, and they really are truly unique opportunities that a department here, right in the center of Washington, D.C., has to prosper and to grow. Now, I know that I don't like having my remarks upstaged by whoever's doing the introduction, so I'm going to say nothing more except to thank our panelists in advance and thank them for their willingness to share their insights and their expertise with us. So now I'd like to introduce Professor Igor Efimov, the inaugural chair of the new BME department. Professor Efimov joins us after 10 years at Washington University in St. Louis, where he was the Lucien Stanley Lapata Distinguished Professor of Biomedical Engineering. He was also director of the Cardiac Imaging Laboratory, which is an NIH-funded cardiovascular research and engineering lab, which studies the physiological and biophysical mechanisms of cardiovascular disease and develops novel therapies for heart diseases. He's also the co-founder of a company called Cardiolin, which is based in St. Louis and Minneapolis, and this company develops pain-free, low-energy cardioversion therapy with a primary focus on atrial fibrillation. A lot of these words will get explained to us when Igor takes the podium. So in layman's terms, he's engaged in engineering the healthy heart, which was the title of his seminar last spring when he visited us. So that's what you will hear about, and he'll tell you a lot more a little later. A little more background on him. He earned his MS and PhD in Russia from Moscow Institute of Physics and Technology, and then he completed his postdoctoral training at University of Pittsburgh. And he then served on the faculty of the Cleveland Clinic Foundation and Case Western Reserve University in Cleveland prior to WashU in St. Louis in 2004. He's a fellow of the American Heart Association and a fellow of the Heart Rhythm Society. Sounds like a rock group, the Heart Rhythm Society. I like it. His engagement in the technical community is very broad and very deep, and it would take me probably another 30 minutes to tell you about that, so I'm not going to do that. I'll just tell you he's deeply involved in many journals, editorial boards, professional societies, prestigious NIH study groups, and he served on expert panels of the World Bank, the Canadian Academies, the British Heart Foundation, the Russian Ministry of Science and Education, the Royal Society of New Zealand, the Swiss National Science Foundation, the National Sciences and Engineering Research Council of Canada, and other international organizations. So he has an immense, broad, deep network of contacts. So Igor, on behalf of all of us, a warm welcome, and also a warm welcome to Igor's wife, Tatiana, who will be joining us in July, and she has a faculty position in the medical school here. And to all of you who've waited such a long, long time for this day, the creation of this new department, we are finally there. So the BME department is now officially launched. And the one thing clearly missing is the champagne bottle to break over the podium, but we'll have to do that later. So Igor, please take the podium.
Thank you. Well, thank you very much, Dean Dolan. Thank you all for coming to this celebration. I'm so overwhelmed with this event, so it's really wonderful to finally start working on building this department. So actually, I just realized that when I moved to the United States in 1992, this was my first stop at the Dallas International Airport before I jumped to the Midwest and then spent 22 years in the Midwest. So now it will be interesting to come back to my first point. Let me start first about talking about research which we do in our lab, and I'm glad to also welcome for the first time my graduate students came today to visit George Washington University. They flew from St. Louis, and for the first time they saw this wonderful building, and indeed they said wow, and they said really wonderful facility. So basically, I only have 15 minutes or so. I'd like to cover so many subjects, and I'm sorry if I will be speaking too fast, but I really want to deliver to you 30 slides in 10 minutes, so which is a challenge. So a year ago, New York Times published this very interesting statistic, as you can see. So in the past 60 or so years, since 1958, when statistics became available, and was kept precisely, you can see that life expectancy in the United States was increased by approximately 10 years. It's a huge achievement in such a short period of time, essentially lifetime of a single generation. And if you see here that essentially across genders, across ethnic background, you see essentially it's all close to about 10 years increase in life expectancy. And if you look at the causes, what exactly was this increase due? So statistics on your right shows that heart disease, which claimed 56 lives per 10,000 population in 1958, now claims only 18. So there was a 68% decline in mortality from heart disease. Also stroke, there was 18 deaths per 10,000 population in 1958, which decreased now in 2010, and statistics was published here, to only 4 deaths per 10,000 population. The decline again of 79%, almost 80% decline in mortality due to stroke. At the same time, cancer, unfortunately, was more resistant to our research, to our therapies. It remained fairly stable. And there was only a small decline between 1990 and now, but still it remains second leading cause of death. So it was a really remarkable improvement in how we treat major causes of death, prevent major causes of death, and basically what was the contribution to this improvement is to a large degree, I can argue that it was due to biomedical engineering. So if you look at what are the major causes of death, let's say 50, 60 years ago, and still now, so arguably one of the major causes of death 100 years ago was bradycardia. So as we age, so our major generator, which makes our heart tick, so-called sinus node, which is a very, very small structure of cells located in this part of the heart right here, this yellow small dot, which generates impulses, and every heartbeat is initiated by this little dot. When it fails, when it slows down during aging, heart slows down, and actually in 4,000 years ago, it was already understood by Egyptians in ancient papyrus Ebers, which stated that when heart slows down and sinks, death is near. So it was already understood so long time ago. So a number of years ago, pacemaker was invented. As you, of course, all know what it is, and it's a major, major contribution to extending human life. Currently, about 1 million patients worldwide receive pacemakers. And pacemakers, as shown here, work really well. However, they are what engineers call a low-definition device. They only have 1 point or 2 points of sensing. They essentially provide diagnosis just based on information from 1 point. And they can also excite the heartbeat only from 1 or 2 points, which is not physiological. And unfortunately, in some patients, it leads to heart failure over a long period of time. Plus, device failure is another problem. More importantly, drug therapy, which was being developed by many, many generations of physiologists and scientists, unfortunately failed. So far, we do not have drugs against this major disease. Another important problem is sudden cardiac death due to sudden onset of ventricular fibrillation. Ventricular fibrillation, in simple terms, can be understood, as you see on the right in this movie, as a very rapidly rotating tornado, which essentially spins around the heart about 10 times faster as compared to what you see here, at about 10 rotations per second. And it essentially spins the heart in such turmoil that it cannot pump blood properly. And again, defibrillators, devices which can send a very strong jolt of electricity into the heart, is really the only therapy available to prevent or stop sudden cardiac death. Again, there are no drugs, unfortunately, despite years and years and generations of researchers studying mechanisms of ventricular fibrillation. Another therapy which is now being developed is called ablation. What it is, essentially, you insert electrode inside the heart, you locate area which is responsible for the onset of this rotating tornado and burn a piece of tissue, eliminating the cause of ventricular fibrillation. But it is still in progress of development. And finally, another major problem is atrial fibrillation. It's really a major issue. As we age, by age of 80, about 10% of us will have atrial fibrillation. And currently, there are 3 to 5 million patients in the United States, and by 2050, will be about 15 million patients just in the United States alone. Unfortunately, development, again, of antiarrhythmic drugs or biological therapies so far did not succeed. Drugs available have efficacy of only 15%, which means 85% of patients do not respond to this therapy at all. And those even who respond have severe side effects. So currently, only ablation therapy is the way to go, and it has some limited success because, unfortunately, single procedure of ablation has a recurrence rate of 75% in 5 years, meaning if you've been successfully ablated, unfortunately, there's a 75% chance that you will come back for another ablation within 5 years. It's in the process of development, and imaging is one of the important issues which has to be developed to locate the source of arrhythmia. Again, you see here movies showing rapidly rotating tornado on one side of the heart of atria, you can see right here, which is responsible for atrial fibrillation and has to be again ablated. So we are working on development of such imaging modalities to guide ablation procedure. Implantable device therapy, which I showed you before for ventricular fibrillation and pacing, unfortunately failed in atrial fibrillation because it's too high energy. So patient who is completely conscious and suddenly receives 300-volt shock to the heart, it's too painful and patients cannot tolerate it. And that's what Dean Dolan mentioned. We started a company based on some of our research to develop a very low energy defibrillator which will be able to terminate atrial fibrillation with very low energy, hopefully pain-free. So recently, development of high-definition imaging and high-definition segmentation techniques led many researchers, and this is data from my collaborator, Professor Trayanova from Hopkins, basically allowed to take CT or MRI images shown here, segment out the heart from it, and create a very precise computer model which reproduces anatomy of that particular patient's heart. And then she takes the next step, and again, using more sophisticated techniques of segmentation, can locate the area which is responsible for the disease, such as, for example, scar tissue or area of fibrosis, which is responsible for the onset of this lethal rotating tornado-like sources of arrhythmia, which are responsible for sudden cardiac death. So she's developing these techniques to guide future therapies, including ablation. But what we thought about, that the same approach, when we have a precise map, precise three-dimensional structure of a human heart, which from a patient who has a disease, we can take advantage of that and build a custom made device. We can build essentially made to the size and to the order of that particular patient using so-called stretchable, flexible electronics platform, working in collaboration with John Rogers from the University of Illinois Urbana-Champaign, who invented this process allowing you to print electronic circuit on a very inflexible membrane, which could be only a few hundred or few tens of micron thick, and then make this membrane exactly in shape, in size of a particular patient's heart. So you can see here a process. So we segment out computationally from medical images heart of the patient. Then we create a mold using three-dimensional printing. And on this 3D printed mold, we print a membrane device, membrane-shaped device. And on this device, we will instrument the device with many different sensors. We have electrical sensors, mechanical sensors, pH sensors, temperature sensors, and also chemical sensors. And this will allow to very precisely document, diagnose the onset of a problem in the heart, including, for example, onset of heart attack or onset of lethal tornado-like pattern of activity, which leads to sudden cardiac death. And then when it is diagnosed precisely in space and time, we can apply very low energy pulses at very high definition, which will terminate the onset of arrhythmia and essentially prevent a sudden cardiac death. And what is beautiful about this approach, as you can see in this particular picture, these devices are actually flexible and stretchable. They do not obstruct motion of the heart. They can be pulled on the heart as a sock, very precisely tailored to the size of the heart, and they will be beaten with the heart without obstructing mechanical function of the heart. So more recently, we looked into a more difficult problem, which is how do you deliver a very large amount of electricity required for defibrillation from such device? And we developed this, again, in collaboration with John Rogers, this so-called fractal electrodes. You can see them shown here. And they allow, we tested application of high energy shock as well. So we will always have a backup to prevent sudden death if necessary to apply high energy shock. So basically, this new platform, which I'm really happy to be able to develop here at GW, and in collaboration with local institutions. For example, last Friday, we went to NIST, National Institute of Standards and Technology, and we found really a wealth of technology available to everyone and to our students and our faculty. So we'll be working essentially on devices which will be custom tailored to a particular patient. You can basically make the metabolic subsystem, looking essentially how heart is fed with fatty acids and glucose, electrical system, looking at electrical impulses, how they propagate, and mechanical system, which allows you to look at mechanics of contractility of the heart. So in these devices will be the focus of our research laboratory in the next years. In parallel, of course, another very important breakthrough which happened over the last 10 years or so, and recently Yamanaka received Nobel Prize for approach which is called cell reprogramming, in which essentially what you can do, you can take a biopsy of the skin of a patient, very minimal biopsy. You can extract cells from this biopsy, skin cells. Then you can apply factors which allow you to reprogram those cells into cell lineage which you need. In our case, we're interested to rebuild the heart. We can build essentially cardiac tissue from that particular patient's cells. Basically, there will be no immunological problems because you will take tissue from a particular patient. And then this tissue can be transplanted back into the heart of the patient after heart attack. So this is first steps. We are working with a number of co-investigators. This is work done in collaboration with In Vivo Sciences, small startup company from Wisconsin, where we are growing very small tissue constructs, about 3 by 3 millimeters, but they already have properties the same as heart muscle in an adult human. So we're also looking forward to develop this technology into a viable therapy in the next 10, 15 years. So this is research. Let me now step back and think about where we are right now in the field of biomedical engineering, which we need to understand the big picture in order to really present our vision, how this particular department in the school will be growing. So I will be very quick. So first of all, so innovation in the last century was primarily done in very large government labs, or very large corporations, and Bell Lab, for example, is a great example. This was done, this very interesting book, The Idea Factory, by John Gertner, describing that, for example, Bell Lab brought to us so many major discoveries which we are now enjoying, telephone information theory, transistors, space satellites, cell phones. Unfortunately, this model is no longer working. As you know, Bell Lab research unfortunately imploded and is no longer producing new ideas. So more recently, a number of theorists in academia introduced concept of innovative university, how universities now will become generators of new ideas. And indeed, big pharma, big medical industry now is looking at the university innovators, basically the ideas originated at the bench in the university as new idea for new products. However, it's not that simple, as I will show you in a second. When universities started designing new innovation concepts, initial idea of administrators was that universities and faculty who will translate discoveries to startups and licensing will bring revenue directly to the university. However, as MIT study shown here has shown, it's not the case. So, for example, in 2011, MIT brought in $1.5 billion in federal funding to basic research and only $76 million in licensing revenue, which is only 5%. It's really a very small fraction. However, the real impact of MIT was not that, was not the bottom line, but how many innovators they actually created. If you look at how many companies were started by alums of MIT graduating every 10 years, what you see here is the following. Those who graduated, for example, in 1950s, as shown in this curve, created about 1,200 companies during their lifetime. Those in 1960s, already about 2,000 companies, and then 1970s, close to 2,500 companies. So essentially, every decade of graduation from MIT led to a steady increase of number of companies started by alums of MIT. And MIT now, if you consider it as a country, would be 20th economy in the world. However, this changed, unfortunately, in the last 10, 15 years quite dramatically. If you look at statistics, for example, what percentage of US companies is less than 1 year old, in 1980, as you can see, was 14%, showing that there is a lot of activity in startup area. Now, in 2010, it's down to 8%. So it's a huge, almost 50% decline. In parallel, there is another problem that a really danger for innovation, patent trolls. So many companies which essentially, instead of creating IP, basically collect IP from different producers and then sue the companies. You can see between 2004 and 2011, there was a 10-fold increase in lawsuits against startup companies and big companies, from 500 to 5,000 lawsuits. So essentially, education in the IP field is critically important in any innovative area, but in biomedical engineering in particular. And finally, funding, NIH funding, which was so generous for so many years and increasing steadily, is no longer increasing. In the last 5 years or so, it's steady and then started declining. So now we have to operate in a completely new world. Then we reached steady state, and we have to really rethink our model of funding science. So basically, bottom line that in the past, our PhD pathway had only one goal. We prepare future professors. And then that's it. So essentially, any other trajectory was not considered appropriate. So now, actually, it's not the case. So we really have to consider that every PhD student has many different professions to consider, including, of course, being a PI at a research institution, but also research in industry, entrepreneurship, science policy, intellectual property, drug and device approval, and production. And based on all of that, I would like to present to you essentially a vision of how this department will grow. First of all, we are in a very good geography. So this is a map showing, and you can immediately recognize geography here, how many essentially employment places in this area. You can see that this is one of the best places for employment in biomedical engineering. Salary, biomedical engineering, again, in the DC, Baltimore Metroplex is also one of the best areas to get a job in biomedical engineering. So another important consideration, I don't know if you can see this table, it's very, very dense, but I'd like to emphasize one important thing. We always refer to being competitive as being in the top spot on US News and World Report. This actually dense table shows top 20 departments in biomedical engineering according to US News and World Report, but also rearranged in a way how much money they actually bring in what is considered to be probably the best marker of productivity, bringing in NIH and NSF funding. And remarkably, top spot on US News is not always top spot in productivity in terms of NIH funding. So for example, I come currently from Washington University in St. Louis. You can see it is number 16 in 2010 at least on US News and World Report, but it is number 1 according to funding by NIH. So it brings in $575,000 per year per faculty. For comparison, for example, Stanford, which obviously is one of the best programs on US News and World Report, number 8 on US News, but it actually brings only very, very small $39,500 per faculty. So it's really very different metrics are now being used, and we have to consider different metrics for growing this department. So discussions and research of our field shows that in order to be competitive, we have to be at least 15 faculty members strong. So currently, we are only 6 faculty members. And essentially, this is what was proposed, and the university expressed support. So we'll be growing, hopefully, by about 2020 to about 15 faculty members. And then in the next 10 years, we'll grow to about 20 faculty members to be essentially on the same level with those top 20 departments of BME. So BME structure, we already had our first faculty retreat, and we decided to essentially establish two administrative positions in the department, and appoint associate chair for academic affairs will be Professor Jason Zara, and Associate Chair for Research and Graduate Affairs, Professor Matthew Kay, who is also a member of our panel. So most important part, and I'm very close to completion, is that we have to use advantages of Washington, D.C. area, and that is essentially proximity of many, many institutions, including regulatory institutions. And one area in which we can clearly compete with any school, including MIT, including Hopkins, including Duke, is essentially regulatory affairs. So we do have next door FDA, NIH, and NSF. We can leverage this expertise and these resources to build a new degree, which will probably start with master's degree and will go to PhD, GWU, BME, regulatory affairs degree, which will include these courses listed here. So we'll train our students in intellectual property development strategy. They have to be able to defend their patents. Regulatory requirements for devices, imaging, drugs, and biologics, and regulatory compliance for the same areas. We will have to train them in good laboratory practices, good manufacturing practices, and good clinical practices. And then, of course, we also have to train them in international regulatory affairs, because now every startup has to go to Europe to get their first approval before actually getting FDA approval. So in conclusion, we essentially want to build core competencies as many other departments in cardiovascular and neural engineering, biomedical imaging and big data, biomaterials and tissue engineering, but we also will have something unique, which is not yet developed at any institution, biomedical engineering and regulatory affairs. There are programs like that in some biomedical engineering departments, but they are only small because they do not have access to the same human resources we have here in the Washington, D.C. area. And basically, this is my last slide. Our long-term goals, of course, will be to successfully compete in the US News and World Report undergraduate and graduate national ranking, but also pay attention to actually objective numbers, which I mentioned, such as citations for publications and funding. We will also have to learn how to leverage unique regional advantages of Washington metro area, having such neighbors as FDA, NIH, NSF, NIST, US Patent Office, but also private foundations such as HHMI, American College of Cardiology, Heart Rhythm Society, and many, many others. And finally, of course, our goal should be to foster the development of culture of innovation and entrepreneurship among our students and faculty. Thank you. Thank you very much. And we'll move immediately to our really highlight of this meeting, of this celebration. So we have truly outstanding panel here today. People who actually, some of them were responsible for development of biomedical engineering field and have been really at the helm of this field from different points of view, from academic point of view, from government point of view, and also from private foundations. So let me introduce our distinguished panel. So first of all, on my left is Dr. Peter Katona, who has a very long and distinguished career, and please read his biography. I just don't have time to read everything, but he has had 3 different hats in his career. One was academic. He was actually, at his highest position, was chairman of department at Case Western Reserve University, where I was also privileged to serve, although at a slightly different time. He was also officer with NSF, who really supported biomedical engineering field in many ways. And finally, he led a very important private foundation, Whitaker Foundation, which was responsible for and helped supporting almost every major biomedical engineering professor. I actually got my first grant from Whitaker Foundation. I'm really grateful. I know Professor Kay also got his first grant. It's really sad that this foundation is no longer here in the same capacity. So now Professor Katona is serving on the faculty of George Mason University, very close from us, and we'll continue working with him. So next from him is Dr. Joel Michaelbust, who is currently Deputy Director of the Office of Science and Engineering Laboratories in the Center for Devices and Radiological Health in the Food and Drug Administration. Next is Dr. Morton Friedman, who was also had a distinguished career in academia, came to us from Duke University, where he was chairman of the Department of Biomedical Engineering at Duke. But more importantly for GW, since he came from 2010, he was really the person responsible for birth of this department. He was really designing the strategy, identifying all the friends of biomedical engineering and bringing them together and identifying all the resources necessary for building this department. And finally, last but not least, is Professor Matthew Kay, who is one of our own, actually, interestingly enough, the oldest faculty member in this department, who was recruited 6 or 7 years ago. And so we'll essentially have a discussion of this panel. So first we'll have several subjects which we'll go over, and we'll start with Dr. Peter Katona, who has really unique insight into the history of biomedical engineering, and he prepared some slides which he will start from.
Well, Igor, thank you very much for the very kind introduction. It's a real pleasure to be here, and I consider it's an honor to have been invited to serve on this panel and to give me an opportunity to give you my congratulations on the establishment of the department. Igor asked me to give you the history of biomedical engineering, which is only about 50 years old, in about 5 minutes. Now, he was very kind, and when I walked in, he said, oh, you can take a few extra minutes. So I will try to do my best to do it in about 7 or 8 minutes. Now, biomedical engineering,
Well, then you have to, I'll just push the button for you.
well, I can.
Just this.
Okay. Well, biomedical engineering, oh, now it's working. Thank you. Biomedical engineering started in the very early 1960s when the first biomedical engineering departments were started both at the undergraduate and the graduate level. And you can see that there has been a very, very strong increase. This particular slide goes on to 2005, but I think it's interesting to see that in the late 90s, there was a tremendous increase in the number of biomedical engineering programs. And if I would show the number of programs that are currently available to students, in about 2015, there are well over 100 undergraduate and biomedical engineering programs. So certainly the field has increased tremendously over the past several years. The professional recognition of the field also increased. And these are just a few examples. The interdisciplinary research, of course, is encouraged by all of the funding agencies. The NIH, National Institute of Biomedical Engineering, Biomedical Imaging and Bioengineering Institute was established in 2001. Biomedical Society has become the lead society for accrediting biomedical engineering programs. And the Bureau of the Labor Statistics says that biomedical engineering is one of the fastest growing professions. And this has been their opinion for the past few years. Now, what is the reason for this tremendous increase? I would like to talk about 2 of those. The first one is the Whitaker Foundation that I think did have quite a bit of impact, especially in causing that large increase in the late 1990s. This private foundation decided that it would dedicate itself to biomedical engineering. It spent more than $700 million on this field. It gave research grants to something like 1,000 new faculty members, and I'm delighted to hear that 2 of them are here. It certainly helped existing departments enhance their programs, and it certainly helped the establishment of many new departments. So I think that certainly the foundation had an impact, but the foundation couldn't have possibly done it without being lucky or fortunate to be active at the time when the biological revolution took place. The Human Genome Project identified the human genes, and it also identified something like 3 billion base pairs that make up the genome. Since that time, there has been a tremendous amount of very, very exciting research that tries to identify the regulatory mechanisms for making a variety of translations going from genes to proteins to cells and to organ systems. And there has been a tremendous advancement in this area. This particular biological revolution also contributed to a changing view of biomedical engineering. The traditional view that we used to give many, many years ago, that biomedical engineering brings engineering rigor to biology and medicine. A young faculty member at the University of Virginia came up with the new view of biomedical engineering. He said that biomedical engineering brings biological rigor to engineering approaches. I think this is the most beautiful way of describing what biomedical engineering is about in my view, and I don't think that I could come up with a more concise definition of what is so terribly important for our field, bringing biological rigor to engineering approaches. I would just like to give you one example of how the biological revolution allowed new research approaches or new even clinical approaches to very important clinical problems. And let's take type 1 diabetes, where, as you all know, beta cells do not produce insulin that is needed, and it is necessary for patients to give themselves regular insulin injections. Now, for the past 20 or 25 years, biomedical engineers with an electrical engineering bent said, well, we'll try to develop artificial pancreas by combining glucose sensors with a computer and a pump, make them very small, implant into the patient, and all of a sudden we'll have an artificial pancreas. Now, this particular approach is very close to coming to fruition. It's not completely there, but there are research projects that show that, yes, it can help patients. There was a new approach, or a different approach, that involved taking beta cells from donors, implanting into the patients, and then these implanted beta cells would produce insulin. There was one problem, that there was a rejection mechanism, of course, if you take donor cells. And then the biomedical engineers with a chemical engineering bent said, well, we'll try to encapsulate these beta cells in such a way that they would be isolated from the body as far as rejection is concerned. This is not quite there yet. One of the recent approaches is the trying to develop stem cells or gaining stem cells from the patients themselves and implanting these stem cells, the pancreas, and persuading these cells to become beta cells and thereby to generate insulin. Certainly what I a little bit heard from Igor talk about some of the approaches in cardiology, it reminds me of the same thing here. Basic biological understanding would help develop new therapies. Now, it turns out that with the new biological approaches, a new view of biomedical engineering, the philosophy of biomedical engineering education has also changed considerably. In the early days, there was a feeling that, of course, biomedical engineers are engineers. They have to get a lot of engineering content. They have to know a little bit of biology also, but there should be a bridge between the two. But initially, the bridge was very flimsy. Later on, it was understood that with increasing areas of engineering, very exciting developments in the life sciences, you have to make that bridge stronger, you have to make it reinforced, and actually allow this bridge to carry two-way traffic. Certainly engineering can learn from biology in addition to engineering helping biology itself. The most recent philosophy is what I like to call the integrative philosophy, where biomedical engineering departments would give students a strong engineering background, but a broad one, and a strong life science background, also a broad one. But the real expertise of the students would be at the intersection of the two. You sum of those two mountains, and you get an even bigger mountain in between. I think that this particular integrative philosophy is very, very important for biomedical engineering, and it distinguishes biomedical engineering from those engineers who are interested in working on biological problems, but have traditional backgrounds. I think that this strong biology background is the one that is specific to biomedical engineers. Now, in the last minute, I would just like to look at the future a bit. I think that biomedical engineers must link basic biology to medical care, and we hear a lot about so-called personalized medicine, and I think that we will be playing a very major role in bringing personalized medicine to reality. I also feel that it is very important that biomedical engineers be involved in the problem formulation and choosing the approach. I don't think that biomedical engineers are technologists who are told by the physician, I want to have a device to do this. I think the biomedical engineer should say why. He or she should be able to discuss the need and might come up with better approaches to solutions. Finally, I think that the biomedical engineer of the future needs to understand societal needs. He or she needs to understand that medical care is important, and I think it is very important that it be better and quality would improve, but it cannot be improved at an infinite cost. So I think that the word, and certainly the word is being used pretty much all the time, it is not cost effectiveness, but it is value. And I think that the biomedical engineers of the future must work on improving value, not only the quality of technological approaches to diagnosis and therapy. I'm very much looking forward to our discussion, and again, thank you very much for giving me this opportunity, Igor.
Oh, thank you, Peter. And I would like to follow on the history track for a few more minutes and ask Dr. Friedman to share. So what was so special about this job when you came here in 2010? Why did you take it? And what was really interesting about this particular neck of the woods? So where you decided to help building biomedical engineering program?
Well, that's a very, very challenging question. There we go. That's a very challenging question. I think that there are a number of aspects to it, I think. First of all, and I was going to talk later about the history of biomedical engineering, there was in existence a biomedical engineering program within the university, in the school of, in the Department of Electrical and Computer Engineering. So there was a biomedical engineering activity here already. There was also an enormous amount of biomedical engineering going on elsewhere in the school. And it seemed that there would be a real opportunity to try to bring these groups together and then interface with the medical and health science people on the other side of the street, who are literally on the other side of the street from the School of Engineering. And that challenge really was one that made it very exciting to work on, because it gave me the opportunity to meet a lot of people in the medical side as well, and to bring engineers together with medical scientists and biologists in the health science schools to do things together that they could not do separately. There's one thing I might add that I had meant to mention after Peter's talk, and that is that this picture we found here, in which people outside the BME department were actually doing biomedical engineering, is really an inevitable event, because biology is so exciting and so interesting that there's no way you can hold that within biomedical engineering departments alone. And it seems to me this generates for a new BME department an opportunity and a responsibility, in that the BME departments, faculty in the BME departments are the ones who know the biology best, who know how to deal with the health services system and with medical school and their culture as well. So I think a BME department, and I think this BME department in particular, has a great opportunity and a responsibility to help the faculty outside of BME who are interested in getting involved in these partnerships and to facilitate interactions and to increase communication. And I think it will not only serve the others faculty well, but it will serve the BME department well, because it will increase the activity of biomedical engineering across the school, which will be a credit to the BME department.
And would you like also to comment on what other partners you've identified outside of GW, which would really be helpful to build this department?
Other departments?
Other institutions.
Other institutions. Okay, within the university and outside.
And within the Washington, D.C. and Washington, Baltimore metroplex.
Okay, certainly. Well, first of all, I think if you think about BME sort of embedded where it is, you have to kind of look around and identify what is around it. And the first thing that's around the BME department is the rest of CEAS. And I've already spoken about that, I guess, in response to the first question. And collaborations in that direction are certainly going to be valuable. But as I also indicated, just across the street are the medical school, people who are interested in healthcare delivery, biology, molecular biology, all the basic biomedical sciences that underlie medical school, in addition to the School of Public Health, the Milken Institute School, with people interested in global health and environmental health. There's just enormous numbers of possible opportunities for collaboration in that domain. And I've said across the street at least 2 or 3 times, because across the street is critical. In my career, I started at the Applied Physics Laboratory at Johns Hopkins. It took me 45 minutes to get to the medical institutions in Baltimore. And I had collaborators there, and we rarely saw each other because it was an hour-and-a-half shot just to get there. I then went to Ohio State University. The biomedical engineering building was just across the river from the medical center, but you still had to get in your car and drive over. At Duke, I was on the first floor, and the medical school was on the second floor. And that makes for collaboration. And we have that here. In fact, we have the medical school and the Milken School in this building, and as well as across the street. So I think that's really going to be an opportunity. And then outside of that, there is all the institutions that Igor showed on that slide. And there are also great opportunities for collaboration in ways other than getting grants. I mean, grants are not going to come to us because we're closer to NIH. Would that were so, but it isn't. But there are lots of other ways we can collaborate. Contracts, for instance, would be made perhaps easier to obtain because we would have better oversight the institutions funding us would have better oversight. Internships, possible job opportunities for our students, teaching. We could have adjunct faculty from many of these institutions that Igor mentioned, and really build tight bridges between the rest of the DC area institutions outside of the academic institutions and BME. So I think the opportunity is really terrific.
Well, thank you so much. And now I would like to turn to Dr. Michael Boss. So what do you think, am I being naive thinking that we can actually really work with FDA and build a program in which our students, unlike many other BME students after graduation, will actually know regulatory process, will know regulatory compliance, and will know good laboratory practices. So before coming here, I had a couple of opportunities discussing this issue with some of the leaders of medical device industry, from Medtronic, from St. Jude Medical, and I asked them this question, would it be really an advantage to have our biomedical engineering students to have this type of training? And they immediately, before knowing where I'm going, told me, where do you find the teachers to teach this type of knowledge? And basically, do you think it's possible to really work with you, with your institution, and get the teachers?
Well, my first question was, what did the people from the medical device industry really say? And I come from an academic biomedical engineering background as well, and so I loved the talk that you gave about innovation. In fact, I feel incredibly honored to be in this company. Going to the FDA, and I think if you took a poll of those device makers and you said, oh, we're interested in innovation, and we think that being close to the FDA and talking to them will help us, I think you probably get a lot of laughing, and that's not the reputation that we have. But let me tell you what our vision is, as stated by our center director, which I think kind of starts to go to this point, and it goes to your point about the manufacturers going to Europe. So our center director's vision is that patients in the United States have access to high quality, safe and effective medical devices first in the world. Okay, so the question is, how do you bridge that? How do you try to move from the FDA being this barrier to the innovative products and make sure that those products do get into the marketplace in the United States so that we can continue that improvement in life expectancy and so forth, thanks to biomedical engineering. And I think the answer really is regulatory science. So I think that so what is regulatory science? I know that I heard in another context that if you take something and you have to put the word science on the end of it, it's probably not. But I think in this case, we're not talking about anything different in the science or in the engineering. What we're talking about is making sure that we ask the right questions, that we look at the right kinds of issues. And I think that if that's one of the jobs that we have in our laboratories, but if we can help to develop this approach across, especially in biomedical engineering programs, then I think that we can start to get to the point where the developers of innovative medical products, as they're developing these devices, think about the kinds of issues that they're going to face when they show up in our place, have them worked out ahead of time, and then we can help answer some of the questions and make that happen. Make things show up in the marketplace in the United States first in the world. And I think a key part of that is both in terms of, I think it would be very interesting to look at a focused program at the master's level to try to generate people who are experts in this kind of a thing. But I think across the entire engineering curriculum, especially in biomedical engineering, to help students understand the kinds of issues that they're going to have in developing devices and then ultimately getting them to the marketplace.
So can you give any examples, maybe you're familiar with other institutions which already made an effort and they approached constructing a curriculum which, in your opinion, would be the closest to what we really need?
Actually, I think that, well, first thing I should say is that the FDA has, over the last few years, established what we call Centers of Excellence in Regulatory Science, CERCES. They're currently are located at Johns Hopkins, at University of Maryland. There's one at Georgetown, and there's now one at UCSF and USC combined. My sense is that in most of those cases, they've focused more on developing research programs. I think they've talked about wanting to develop a curriculum, but I'm not really aware of a curriculum that I think would really work. So I think this has the opportunity to be, right at the forefront of trying to solve that problem.
Well, and I really hope that you will be our partner in developing this curriculum. I am, as I mentioned, familiar with one curriculum from UCSD, but they only managed to recruit enough faculty for a certificate program. It's just not enough experts in the San Diego area to build a master's program.
But I think one aspect of that is that it's one thing to understand the admittedly arcane rules and regulations and so forth that we operate under, but I think it's another to broaden that focus a little bit so that you're really thinking about the full scope of the kinds of questions. And so I think in my own mind, I'd like to think about it in terms of science in support of all sorts of policy and regulatory decision making, so that you can look at the kinds of questions that third-party payers may have, for example, or to look at, one of the things that we've recognized in trying to move our work to the point where we're not just protecting the public health, but enhancing the public health by trying to move things to market more rapidly, is that we have to actually look back further into the development process. And I think that needs to be a part of what we do, so that we help companies understand, have the tools, have test methods and so forth, so that when they're at that point of deciding whether or not the device is ready for a clinical trial, that they can make sure that trial is focused on the right thing. So I have more understanding from the bench testing and from computational modeling and this whole realm of things, so that you can not just jump blindly into a clinical trial, but really make sure that trial is focused on the most critical questions. So I think that a program like this could develop, and by inculcating it across the curriculum, could, I think, develop a cadre of engineers that could really be helpful to industry in a lot of different ways.
Well, also we think not only to industry, but also to FDA, ultimately. So we also hope to have this as an employment opportunity for our students.
I'm not sure that we've ever really developed the statistics, but I think that it's likely that the Center for Devices and Radiological Health, CDRH, is one of, if not the largest concentrations of biomedical engineers in the U.S. government.
Oh, thank you. Yeah, so and now let us turn to research. So we have, as I already mentioned, the oldest professor in our department who has been here longest. Basically, Dr. K, so your experience now here is already, what, 7 or 8 years at GW?
I came in 2006. I started a position in the department.
So you know probably the environment for biomedical engineer here the best. So can you comment in your experience, maybe listing number of collaborations with different institutions and different departments here at GW? So where do we go from here?
Sure. And just to clarify, I think I'm the oldest member of the department on the panel, because we do have other members in the department that have been here much longer than I have. We have 6 faculty members in the department. So I started my faculty position in 2006, and as a couple of other panel members have mentioned, collaborations within the university are critical, especially with the School of Medicine and Health Sciences, with the GW Hospital and the faculty at the hospital and the medical faculty associates. And now we have a GW School of Public Health. I think that having the School of Engineering located within, within one city block, within these very productive schools is critical to our success, especially for the research success in the department. When I came in 2006, it was my collaborations with professors in the School of Medicine and Health Sciences that really helped me to get a good running start in my research program. It was through my collaborations with professors there in the medical school that I was able to get funding from the American Heart Association, and then able to get funding from the NIH with a large-scale 5-year grant from the National Institutes of Health. And having those collaborations was critical to show that I had the clinical and the biological expertise on my team to do the work that I was proposing to do. We have other faculty in the department who also have very strong collaborations with faculty in the School of Medicine and Health Sciences and the medical faculty associates, and probably forming collaborations as we speak with faculty in the School of Public Health. So I think that growing and cultivating those collaborations is a very important point in building our biomedical engineering research programs. Some of the projects that our faculty are working on in the department involve various imaging modalities as well as device development. We have projects where faculty are working on thermal imaging for breast cancer detection. We have faculty working on detecting epithelial cancers using optical coherence tomography. We have faculty working on using ultrasound for therapy, for cancer therapy, and for drug delivery. We have faculty, including myself and Igor, working on high-speed fluorescence imaging of cardiac arrhythmias and electrical activity and metabolism. And then we also have faculty building small-scale microelectronic systems and microfluidic systems using optics for building new biosensors and for building new diagnostic systems for detecting disease. I think that Igor very nicely mentioned some of the highlights that we would like to focus on in the future and in our faculty hiring and in building new research programs. And some of those initiatives are associated with using new technologies in microscale and nanoscale technologies to build distributed sensor arrays that can be implanted in organs or used in ex vivo studies to measure physiological functions from hundreds or thousands of sites. There are new technologies coming online that are opening up new possibilities for biomedical devices that have really never been there before. Building collaborations with partners at the National Institute of Standards and Technology to help us build these devices, working with collaborators at the medical school and at the hospital will help us sort of gain that clinical insight into how the devices can be really used to treat diseases. So, I think that the opportunities for research are numerous, and there are many strengths that we hope to build upon to launch into new areas that we haven't been able to do before.
Yeah, and I would like to actually emphasize again, so we had our first faculty visit last week. Half of our faculty, which was 3 faculty members, went to National Institute of Standards and Technology, and I was really impressed what facilities are available to everyone, actually, even to private person. Mm-hmm. But what is really remarkable, the expertise and level of facilities, and also their willingness to help in developing the whole manufacturing process without actually participating in the intellectual property. So it's really almost free help. And then, of course, having FDA next door, which can help before you go into a clinical trial to really understand what is your endpoint, how you want to design a proper clinical trial. And this is really a unique type of resources which is not available in any other institution.
I think one aspect, though, of this too is that, there's a lot of biomedical engineering in the regulatory work that we do, but that's also true in other regulatory agencies. So I think EPA, for example, should be a fertile place to look. And in fact, I think that it was in EPA that they first invented this term of regulatory science. But also Department of Transportation, trauma biomechanics, and so there's this city is loaded with regulatory agencies, and they should be using science, and in a lot of cases it should be biomedical engineering science.
Well, actually, another aspect which I didn't mention and didn't come up in our discussion is the fact that we have U.S. Patent Office next door, and also U.S. Federal Court of Appeals for intellectual property cases, which means every major law firm is within 10 blocks from us. And I know for a fact that many biomedical engineering students, before they, for example, go to graduate school or to industry, they spend some time at the U.S. Patent Office. And having a great law school right here at GW, and specifically with expertise in intellectual property, also gives us an opportunity to build a unique program to integrate in our biomedical engineering curriculum intellectual property strategy development, as I put it in this course. So would you like to add something?
Yes, I would just like to mention that certainly it is marvelous. You have the medical school, you have a variety of federal government institutions, but also I would like to mention that there are 3 other biomedical engineering departments, something like 20 miles within here. Some of those departments have been around for a long time, some of them have been not around for a long time, and I think you might find some expertise that would complement the expertise here. So I would just put in a good word for exploring potential collaboration with the educational institutions in the vicinity that have biomedical engineering expertise.
Mm-hmm. Very good advice. Yeah.
If I could add something to what Peter said, we have made some overtures to some institutions around here, and we do have some collaborations. We had several workshops with Georgetown, which has, So we've had several interactions with Georgetown, home-and-home workshops. Georgetown is a particularly attractive collaborator because they have a medical school and no engineering school. And we are close, so it looks like they might be people who would be good partners and might be interested partners with us. We're in the process, we hope, of building a collaboration with a faculty member at Catholic. And we have already formed through the Office of Entrepreneurship in the Vice President for Research Office, a partnership with Virginia Tech, Maryland, and Hopkins on what's called an I-Corps program, which is perfectly appropriate to what we're talking about here, as a matter of fact, which is teaching faculty how to become entrepreneurs, basically. So, but it's a very good point, and I think we should not omit those opportunities.
And maybe last before we go into the questions, but not least, I would like also to add another opportunity which I didn't have a chance to comment on. Dean Dolan mentioned that I was really privileged to serve a number of times as an expert on a panel of World Bank. So I worked on helping essentially developing countries develop their strategy for innovation, entrepreneurship, biomedical research. And during this work, I have seen many instances of unmet needs for developing inexpensive diagnostic and therapeutic tools for developing countries, which are clearly underserved. And I have seen also a number of projects, primarily from Europe, developing such tools using novel electronics platforms based on Android, for example, devices. And clearly, having World Bank just across the street, we can really build such a program for international assistance in the third world. So I would like now to turn to the questions. So please, do you have any questions to our panel? There's a microphone over there.
Hi, congratulations on the department. I guess I more have a suggestion than a question. A lot has been said about collaborations with medical schools and regulatory agencies and whatnot, but it seems to me that most of your graduates will not become faculty members. That's just the nature of the statistics of this field. And you said there's a lot of companies that hire in this area. And I would just recommend that once you start putting together the curriculum and courses, often the departments kind of come up with these courses on their own and what they're going to teach, but they don't really consult a lot of companies on what they should teach. And it would seem to me that another panel you should probably put together is a panel of these company leaders that run these companies and just simply ask them, what should we teach? Because often these graduates come to these companies and they have to be often retrained or additionally trained for jobs that they will be doing. So that's all.
Thank you. Yeah, it's a very good point. And actually, I know that a couple of former chairs of leading biomedical engineering departments have something to say about it.
Yeah, that's an excellent point. I think the whole, particularly graduate education, there's also at the undergraduate level, but in graduate education, it's becoming a very different situation. The usual career path would be to get your PhD in biomedical engineering and then accept a position in one of the new Whitaker-founded or recently Whitaker-founded departments, get funded by the NIH, and smooth sailing. Not so anymore. So I think that we really do have to think about graduate education aimed at corporate and startup employment. And this works very well with this notion of teaching innovation. But I think it may have even more dramatic effects on how we look at graduate education. When we say we have a successful program, or how we identify criteria for graduation, how we judge whether or not a dissertation is appropriate, I think all of these things may change as we see more and more of the graduates not moving into research and academic positions, but into industry and startups.
Peter, would you like to add?
Yes, I would like to echo what you've said from 2 points of view. One is departments typically have industrial advisory boards, and I think it is really important not necessarily to tell the department what to teach, but to give them some feedback. So I think your point is exactly well taken. The second reason why I think it is very good to have an industrial advisory board, because ABET, the accreditation agency, pretty much requires that departments have this advisory board. And when the ABET visitor comes around, he or she is going to ask, who is on your advisory board? Are there any industry people on it? So I think that you really probably need to have that also from the ABET point of view.
Yes, and we actually already engaged a number of leaders from medical device and imaging industry, and we will probably form our industrial advisory board within the next few months. Yeah, thank you. So any more questions? I've seen a question from here.
Yes, my question kind of cuts across both engineering and regulatory, which has to do with the, yeah, sorry. So my name is John Holmwood, by the way. My question cuts across both the engineering aspects and the regulatory aspects of bioengineering and biomedicine. And it actually has to do with the field I work in now, which is cybersecurity. And by way of example, just today we were looking where I work at a newly disclosed vulnerability in an operating system called Linux, which is very widely used everywhere, including in medical devices. And so I'm wondering what is going on in the regulatory area when it comes to certification of devices that can be placed into the clinical setting, into the home, wherever they are, into the person's body, when it comes to the cybersecurity aspects of them.
Would you like to take it?
Sure. This is a really burning issue for us. We spend hours every week talking about it, and there are multiple aspects to it. And it really is true, I think, just as you're saying, that many medical devices are vulnerable, and we don't generally know it. They're not usually under attack the same way that our networks are and so forth, but they do have vulnerabilities, and they're also and those vulnerabilities are enhanced when they're connected to the networks and so forth. The FDA does not typically certify any kind of a device for any purpose, but we are definitely, we have developed guidance for industry on the kinds of questions that we hope that they're looking at, and we're actively looking for how we can play more of a role to try to head those things off from the beginning in our pre-market evaluation of devices, but also how to respond when these things show up in the post-market. So it's definitely an important aspect, and I think potentially another point of collaboration for a department like this with other parts of SEAS and a lot of other agencies around the community.
Thank you. So, any more questions? Jason.
Just to go back to Matt being old. I've been at GW longer, but that is.
I'll give you that.
I was actually fortunate enough to have Whitaker funding for my graduate studies, so I wasn't old enough to get a research grant from them because they were gone by then. But I think that these things are, and Whitaker was a huge jump to these things. And I guess I have the question is, and I get this question when I do undergraduate recruiting from parents, is how much, and Peter, maybe you have input or more, how much do you think there's room to keep growing as we skyrocket upwards in enrollments and programs around the country? What's the ceiling for this, or is it endless? Are we in a bubble?
I think this is a superb question and something that I think about quite a bit. And especially since Whitaker provided a lot of jobs, and those jobs are not being provided anymore. I think that there are two issues, and there are two kind of semi-solutions. One is that biomedical engineering should go beyond the typical Whitaker initiative of supporting departments, faculty members. And I think somebody already mentioned that organizations, industry, and government increasingly recruit biomedical engineers. So we should not look at, I think, biomedical engineers the old-fashioned way of the person who is going to be trained to teach more biomedical engineers. I think there is an issue there because clearly there are many jobs, but on the other hand, there's a lot of competition to these jobs. So I think that point is very well taken. The second way to deal with that, I really think, is excellence. I think that when institutions hire people, they really try to hire the best qualified ones. And as a result, I think a department of bioengineering or biomedical engineering needs to train students in a way that they will be really excellent. So I think it is marvelous to have a vision for the department. I hope that you will be training biomedical engineers who are going to be somewhat different than the other 100 other departments are training. And I think you really have to kind of identify yourself, what you stand for. I remember that back in Whitaker's days, we thought that it would be nice to come up with a curriculum that would be the right curriculum for all biomedical engineers. I'm really delighted that we absolutely failed in that effort. I think that the beautiful thing about biomedical engineering is that you can combine some aspects of biology and some aspect of physiology, and there's an intersection over there, and there's a whole range of engineering, there's a whole range of biology, and the intersections are really numerous. So I think that identifying what is unique about the background for that particular biomedical engineer and indicating that, yes, I know this type of intersection between engineering and medicine, while the other 1,000 biomedical engineers might have expertise somewhere else. But yes, I do worry about it, but I think excellence is the way to deal with that.
Yes, please.
My first comment to respond to Jason's first point is that I was too old to get Whitaker funding, but I had graduate students who did. But in terms of that question, I was on the faculty far enough back to remember a period when students would be coming to us saying, there are no jobs in biomedical engineering. We faced that for a number of years, but I think about the time that the graph that you showed started to take off, we started to get real penetration into industry and put a lot of students into the medical device industry and other aspects of the biomedical space. So I think that we've probably just begun to penetrate that whole arena. So it's not only that the medical products business ultimately can't do anything but grow, I think. I mean, but also that there's still a lot of capacity that we can penetrate with biomedical engineering students.
Well, I think also I would add to that, in addition to conducting research in the United States, I'm really privileged to collaborate on a number of projects in Europe, in particular in France, in England, in Germany. And I can see that there is a huge opportunity actually in Europe and beyond the United States. Biomedical engineering as a field is only growing there. And in fact, Whitaker Foundation is not gone yet. Whitaker Foundation is still funding international fellowships. In fact, one of my graduate students just went to France, to Bordeaux, on Whitaker Foundation fellowship, and which means essentially foundation did recognize this particular bridge. So there is an opportunity in Europe and also a bridge for growth and for new collaborations. But also I would like to add that I did recognize also probably some time ago already that training just new biomedical engineers for academia is not what we're supposed to do. In fact, I recently looked at my own statistics of my own graduate students who graduated from my lab. And it's about 50-50 between industry and academia. And I'm equally happy when I see, and equally proud when I see one of my former graduate students, Crystal Ripplinger, who went to academia and she got her first major NIH grant, R01, within only 3 years upon her appointment as an assistant professor. And also seeing another graduate student, Alex Sambelashvili, who went to Medtronic, and he is now one of the managers responsible for development of leadless pacemaker, which is a true breakthrough in technology in the next several years. So are there any more questions, please? Yes, please.
Yeah, you just mentioned something that...
I'll just give you a microphone.
You were talking about where your students are going to work, and you mentioned academia, and then you mentioned industry. But doesn't hospitals hire biomedical engineers? Because you have not mentioned that, and I would hope that you will be collaborating with medical physicists. I am a medical physicist, and with clinical engineers, which I'm never sure what connection they have with biomedical engineers, and that perhaps somebody in the panel could clarify for me.
Maybe I'll take the first crack, but basically you're absolutely right, and I'm sorry we kind of omitted that. I'm involved with a number of clinical societies. For example, I served for several years on the program committee of Heart Rhythm Society, which is a major cardiac electrophysiology group with about 15,000 attendants on annual sessions. And I recall statistics that scientists only make up about 5% of attendees of the conferences. Physicians about 60%. But the next big group, much bigger than scientists, actually is allied professionals, including a very large number of biomedical engineers and physicists who work in this field, primarily in the hospitals. Yeah, so it's indeed a very, very large group, and we graduate many of our bachelor and master students and PhD students who go to hospitals to develop new methods, new therapies, and also to work with physicians shoulder to shoulder on essentially therapy side. Yeah, so do you have to add something?
Yeah, I think on this area in general, NIH recently recognized, and I can't remember the name of the program that they developed, but they came to the realization that it's actually a small percentage of newly graduated PhDs who end up going into academia and teaching and doing research. And so they've been trying to encourage graduate programs especially to help students understand the broad range of opportunities that they have and to give them opportunities to see what's available out there, but also to recognize that some of what they need to learn, they're not necessarily going to learn in biomedical engineering graduate school. So things like some aspects of budgeting and project planning, and along with, just to piggyback on this comment, and we've kind of said it here, but government sometimes requires a whole different skill set. And if somebody just during graduate school thinks they want to do that, then maybe there's a few extra things they need to learn along the way. So it's definitely something that the program needs to keep in mind, I think.
I think this is an excellent question, and it really makes me recall my experience at Case Western University in the 70s and the 80s. At that time, there was a very specific master's program at that university that trained clinical engineers. And that particular program no longer exists. And most of the biomedical engineering departments do not have a clinical engineering program very specifically. It turns out that some of the biomedical engineers go into this area, but it is quite rare that they would go to a particular hospital. I understand that these days there are some companies that provide clinical engineering service to different hospitals. In other words, you contract with a hospital and you provide service whenever they are needed. I think hospitals very often recruit not clinical engineers, but allied health technicians, and very often technologists are the ones who fill the role of the clinical engineer. They are the ones who make sure that the particular equipment is working. They are the ones who help order the right equipment. And they are the ones who are called upon the first time if something is broken down. But I think your point is well taken, that current biomedical departments do not emphasize that. I think some of the health science colleges have much more presence in hospitals who train technicians over a 2-year period, and those are employed by hospitals throughout the country.
Well, there are actually examples of this type of engineering activities, biomedical engineering activities in major hospitals, such as I've been privileged to serve on the faculty of the Cleveland Clinic next door from Case Western, and there is a big biomedical engineering department there, which actually is primarily medical physicists, engineers who work with physicians on building prototypes, not just fixing equipment, but building prototypes of devices or new tools. For instance, one of the most impressive programs they have is surgeons can come up with the idea of a particular tool for surgical treatment, and there are 3D printers available with help of biomedical engineers. They can actually build a prototype within a day and put it essentially to use. And then licensing of such ideas is a very much streamlined, so they can achieve a workable prototype within just a few days. It's really remarkable. And I know such divisions exist in such hospitals as Cleveland Clinic, Mayo Clinic, and many others. And I think Mort wants to add something.
Yeah, there's another group of sort of closet biomedical engineers that you'll find in hospitals, and they're called physicians. BME is about the best undergraduate program to go into if you want to get into medical school. So a lot of physicians have BME backgrounds, and you'll also find them in medical physics. There's a lot of good master's programs in medical physics that take undergraduate biomedical engineers and place them in radiology departments.
Well, thank you. Thank you so much. And I'm sorry but we're already 10 minutes over time, so I would like to conclude and thank our panel for a beautiful discussion.
Well, let me wind down the proceedings by saying thank you also to the panel and welcoming you, Igor, again. We're looking forward to great things from this department. I want to thank all the guests who came. I hope you enjoyed this. You are the first group, I think, at least in C's, to seriously use the Lehman Auditorium, so write that in your diary or on your Facebook page. We're a famous group. So please join us for a reception outside right now, and after reception, if you haven't been around this building, take a look. Okay? Thank you very much.
Good.